Okay, so 9.2. Problem 10. How many ways are there to three color the end beads of a baton if adjacent bands must have different colors? Okay.
So I just want to make sure like I'm visualizing the situation right in my head. So we've got like are we talking like baton, like some sort of stick looking thing with different bands of colors on it? Okay.
Mm-hmm.
Okay, so there's N of those, and then we have to make sure we're coloring it 3 colors, but we can't have 2 colors the same next to each other.
Yeah, and there's
Okay.
actually let me see here. That was 9.2, right?
Yeah.
Okay, so you have Burnside's theorem in your back
Right.
point. So there's a problem that kind of deals with batons. There's actually
Oh, yeah. Example 1.
example 1 and example 2.
Oh, yeah.
They kind of talk about like what symmetries there are, and they're fairly obvious. It's just um I don't think that they want to allow you. Well, actually, reflection for a baton, reflection would just be the same as, would that be the same as 180-degree rotation? I think it would be, wouldn't it?
I think so, because the color goes all the way around.
Yeah.
So I think,
Yes. If
so
we
I think you
reflect
basically
it,
can have it go like this or like that.
and that's the same thing as going like that.
Right. Okay.
So, uh, so really the only, I mean, the group is fairly trivial in this case.
Right.
The identity and 180-degree rotation, and that's it.
Okay.
Now, on the last lecture, I don't know if you've had a chance to watch. Did you watch the one from today yet?
Yeah.
I mentioned that the theory itself does not require us to always like have all possible symmetries.
Right.
Anything, so long it's just a group.
Right.
And the same thing is true. What else did I say? Did I say anything else about that? Like, oh, the number of colors, right? So the number of colors, it doesn't matter, right?
Right.
I can go wild with the number of colors. I could also impose the kind of colorings that I want to look at.
Okay.
Does that
Like
make
in
sense?
this, like in this case, you can't have adjacent colors be the same.
Yes.
Adjacent bands be the same.
And that changes T a little bit.
Right.
You can still just kind of strategize. You could at least initially think about it, in sort of a wild-eyed fashion of just like saying, well, I don't know, how many colors did we have? 3, something. And you could just go 3, okay, the first bead is, there are 3 possible colors, yes? And if I want adjacent colors to be different, and I go to the next bead, and how many options would I have for that color?
2.
2.
Okay.
So it's basically going to be 3 times, instead of just like what we've been doing so far and going 3, 3, 3, 3, 3, 3, 3 like that.
Yeah.
We actually impose a little bit more structure on the type of coloring we want to see. And we just go 3 times 2 times 2 times 2 times 2 times, right? So then after you've done the first bead, the other ones, there's just going to be 2 colors after.
Okay.
So we have way more freedom than we realized. Like all of the general theory that we were doing was allowing us to take any group of symmetries, any number of colorings, and we can impose any kind of coloring restrictions that we want on the front end. And we just have, and then Burnside's theorem is going to take care automatically of all the different symmetries, ways of kind of rotating that thing around or flipping it around or whatever you want. And it's going to pick out the ones that are truly distinct under that symmetrical, under those symmetries in the group. So the size of T is slightly different here, right? It's 3 times 2 to the n minus 1, basically.
Okay.
That's the total number. But then you're going to have to think about Well, which ones of these are going to be fixed by, well, first of all, it's obvious how many of them are fixed by the identity
Right.
of them.
All of them. Yeah.
Then you would have to say, how many of these are fixed by 180-degree rotation?
Okay.
And in that case, what you're going to have to say is, well, if it's going to be fixed by 180-degree rotation, the two ends had better be the
The same.
same color.
Okay.
And then the
We're
ones
just
that
gonna
are
work
in
our
one
way.
end had better be the same.
Right.
Yeah.
Okay.
So this is why in the next section we're going to go crazy with like, oh, so really all that matters are things that are like in kind of a cyclic paradigm with one another.
Okay. Yeah.
Like if there's a piece of the thing that's rotating to here, which in turn is rotating down here or something
Mhm.
like that, that's what really determines how much freedom I have in assigning colors.
Okay.
So yeah, when you use Burnside's theorem, you're just going to have to think about, you know, basically you're only going to have to go like halfway into the
Right.
thing, and you're only going to have freedom on those beads. And if it's going to be fixed by 180-degree rotation, then the other ones are going to be determined. And you're going to have to fiddle in the middle a little bit because
Right.
of what?
Well, I mean, it seems like you can either have like two in the middle
Uh-huh. Or one.
or one. Yeah.
Yeah. So that's
But if
the
there's
odd.
two in the middle, it won't work because you can't have two of the same color next to each other.
Ah, yeah.
I mean, I'll still have to fiddle with it some, but I think
Yeah.
with the restriction we have, it only works if we have an odd number of.
That's true. Yeah. So anything. Oh, right. So does that mean in the even case? So what's going on here? If you have an even
I think if it's even, none of them are fixed, right?
I guess that's probably true.
Because once you get into the middle, they're going to be different. You know, the two that are touching in the middle,
Yeah, right.
and then when you swap them, that won't
So
work.
psi of 180 degrees for the even length bands is 0 because of those two in the middle. That's kind of weird, isn't it?
Yeah.
Is that really true? Wow. I don't know. You could always play around with some small examples and convince
Yeah.
that that's the case. But I think that's probably true. And it's all because of those two that reside next to each other in the middle.
Right.
Going to prevent them from being
The same. Yeah.
from being the same. Yeah.
Okay.
Wowee. Okay, that's cool. Isn't this stuff sort of it's sort of amazing when you kind of think about it.
Yeah.
But it doesn't seem like you should be able to do this.
Yeah. You kind of look at a problem like that and you're like, it wants me to say what? And then, you start thinking through with the Burnside stuff and it's like, oh, okay, that's actually doable.
Yeah, it's extremely powerful. So yeah. So you have some other questions?
That was the only one I had for now. I mean, I just submitted tomorrow's homework, so I've just started looking at this homework. So that's all I had for now.
Okay. Well, I'm almost done. I mean, the test took me an incredible amount of time to grade. So I'm almost done. I think I vaguely recall that I just might have finished grading yours.
Oh, okay. I think I might have seen that a grade got put into Canvas, but I didn't see what grade it was. So.
Oh, okay. Yeah. So I mean, I'm doing my best to give as much feedback as I possibly can in Speed Grader. So I mean, you can go read that and ask questions about certain things. One of the problems. I mean, do you remember it was like mathematics, and you had two T's and like two M's and two A's.
Yeah.
and you wanted the both T's to come before both A's, or both A's to come before both M's, or both M's to come before the E. And I think there was one of the on that problem, there might have been an issue that you were having, because I mean your approach was in general pretty sound.
Okay.
Like there was an issue I remember when I was looking at yours where it was like, I'm not quite sure if you were basically doing some kind of donut distribution thing or something, and then you wrote
Okay.
some things or something, and I'm not quite sure that one of the cases was working quite the way
Okay.
you thought it was. At least it didn't match up with what I had, and I had done it like multiple different ways.
Yeah.
And so that was messing up your count a little bit. And there was another one. Oh, that recurrence relation one. You had, man, that first one, you had a,
I had a rough time with that one.
I mean, you're like doing linear algebra to try to solve for the coefficients.
Yeah, it was not working out well for me.
I think it actually ended up working. You got the right
Okay.
answer,
Okay.
but what was weird was I couldn't figure out how your recurrence relation was working. And then I was like, oh, I see why it's working. Because sometimes you can have different recurrence relations that
Oh, okay.
are the same thing.
So if I'd found a better recurrence relation, I probably could have found easier coefficients.
Oh yeah, so I wrote it in there. It was just an was like twice the previous term plus twice the 1-2 previous.
Okay.
Because you just, what was it? It was like AA wasn't allowed.
I think so, something like that.
Was it AA? Just AA wasn't.
Something like that. Yeah.
So then all you have to do is say, well, if the thing starts with B or C,
Mhm.
then who cares what's after that?
Yeah.
So that's twice A and minus 1.
Mhm.
On the other hand, if it starts with A, then I had better see B or C in the second position. If
Right. Yeah.
B or C, then I have complete freedom in the last n minus 2 slot.
Okay.
So that's why it's
Yeah.
just 2a and minus 1 plus 2 and a and
Okay.
2.
Yeah, that seems like that would be a lot easier to solve.
That was just I mean, what was weird is one of your coefficients went away. It was like 0.
Yeah. Yeah.
So that should immediately tip you off. Right, that should tip you off that like, oh man, what does that mean? I mean, that probably means that I could have had a quadratic or something.
Yeah.
You could, right? There was a quadratic, namely coming from that one. But what was interesting was the recurrence relation that you gave in A was actually the one that worked for B. So the relation for A was actually the one that worked for B, and whatever you had for B, you were missing something just slightly.
Okay.
That one. I didn't ask you to solve for or anything there because it was a cubic.
Yeah.
That didn't prevent that didn't stop you in part
it
A.
really did not.
Yeah, that was the one where I actually did solve it, and I was like, oh man, that was horrid, because I did have to use like linear algebra for B, and then I said, I'm not going to make them solve for the coefficients. And I just threw that one out, or all I did was say, just give the recurrence relation in the general form of the thing. But
so wait,
you were not. Yeah.
So did that mean you could use the same recurrence relation for both of them if the one I had in A was the one that worked for B?
Yes, but
Okay.
But I didn't know that was true until after I saw your test. I mean, so I think, so there was 2 I said that couldn't happen there. What was it? It was like A, do you remember what it was?
I want to say it was ABB and ABC, maybe?
Here, I can look it up right now, just a sec. Here, I can look it up. ABB
Mhm.
ABC are not allowed. So, yeah, okay. So ABB or ABC were not allowed. So yeah, what you could do is you could say, well, um, hmm, uh, what if my sequence starts, okay, what if I just went wild and let the sequence start with anything, A or B
Mhm.
or C? Um, then uh, that's like 3 times A and minus 1, right?
Right.
But then I counted some bad ones.
Yeah.
Oh, okay. So here, you're right. So what you could do is you could say, okay, if it starts with B, hey, cool. That's just A and minus 1, right?
Mhm.
If it starts with C, cool.
Mhm.
Another A and minus 1. If it starts with A, okay, and you just kind of finish it with A and minus 1 ways, then that's not quite gonna work.
Right.
What are the things that you don't really want to see if it started with A?
Well, you don't want to see next a BB or a BC
Yeah.
sequence.
So you need to subtract off those two cases.
Okay.
So minus 2 times A and minus 3. Does that make sense?
Okay.
3
Yeah.
A and minus 1 minus 2 A and minus 3, which is exactly what you had in part A. What is going on here? And so yeah, there it is.
Okay.
Occurrence relation for that one. Um, Turned out it worked out fine. But the initial conditions were different in A versus B,
Mm,
which
right.
gives you a different sequence of numbers, even though the recurrence relation is the same. If that makes
Right.
sense.
Yeah.
So anyways, thought I would
Hmm.
just kind of point that out.
Yeah.
Yeah. Anything else?
That's all I had.
All right. Well, hey, thanks for coming in and
Yeah. Oh, thanks so much.
yeah. All right. I guess we'll stop then. All
All right. Have a good
right.
night.
See ya.